Buenos días. Pues vamos a continuar con las sesiones del Seminario de Economía y Complejidad. Pues en esta ocasión tenemos la presentación del doctor Fernando Pascual dos Santos. Él trabaja en el grupo de sistemas artificiales socialmente inteligentes del Instituto de Informática de la Universidad de Ámsterdam. El grupo se centra en la inteligencia artificial centrada en la ciudadanía y la comunidad, que tiene como objetivo reducir la desigualdad y promover la igualdad de oportunidades en la sociedad. Pues yo le agradezco mucho al doctor Santos por su gentileza de participar en nuestro seminario y lo dejo con él. Muchas gracias. Adelante.
Sí, muchas gracias por la invitación. Es que me voy a cambiar para inglés. Perdona. Ok. Pero si tienes preguntas en español, puedes. Yo consigo comprender, pero no hablo muy bien. Okay, I'll just share my screen now. Okay, hopefully you can see my screen in correct mode. Okay, is it the case? Can you see in full screen mode?
Sí, se ve bien, no hay problema.
Okay, thank you. Thank you very much for the invitation to present to you today in this really interesting seminar series on economy and complexity. As Professor Ricardo mentioned, I'm Fernando Santos. I'm an assistant professor at the University of Amsterdam. And today I will present you on link recommendation algorithms and polarization dynamics on online social networks. And this is a joint work with Iftach Lelks that I believe presented to you in March, and also joint work with Simon Levine at Princeton University. I will introduce some concepts on social media platforms, also opinion dynamics and networks. And I am aware that you are going to learn more about network theory next week. So please, if there's any concept that sounds a bit more confusing, feel free to interrupt. Actually, feel free to interrupt at any time. I was telling Ricardo and Rosa that the talk should be not that long. So there's time for questions, there's time for clarifications. So feel free to interrupt anytime. Also, let me point out that the model that I'm going to present has some similarities with a model that Alessio Franci presented in April. So there's some connections between these works. Okay, so first let me give you a quick summary of what I will present. So I'll start from the motivation that nowadays political opinions are influenced in online social networks, on Facebook, Twitter, in a lot of platforms where we debate with others and we are exposed to information about politics. At the same time, interactions in these platforms are mediated by algorithms. So there's quite some work on algorithms that filter content. And there's another class of algorithms that I would like to explore today with you called link recommendation algorithms. So these are algorithms that are used to recommend connections to users. And the main question that I will pose today is, what is the impact of these algorithms in opinion polarization? To tackle that question, I will present a model of opinion formation on a dynamic network. And I will present that model, I will present some results, and I will also take that opportunity to give you a brief overview of models of opinion dynamics on networks. And again, I'm aware that you will learn more about networks and network theory next week. So this will just be a very quick overview, but feel free to ask for clarifying questions. And in the end, with these models and with the results that I will present you, we will conclude that indeed these link recommendation algorithms can impact opinion polarization, and they seem to be actually an important mechanism that can be used as an intervention mechanism to control polarization and radicalization in online social networks. Okay, so this is the whole plan for the presentation. And in the next hour, I will just go with more detail into each of these points. And again, feel free to interrupt anytime. So I don't think it is a surprise to anyone here that nowadays online social networks play an important role in shaping political opinions. This is some data from the Pew Research Center in the US, pointing out that nowadays the majority of adults get their news from social media websites, and this corresponds to an increasing trend. So more and more people tend to use social media websites to read their news, to interact with others. This happens in the US. This is data from the US, but the same happens actually in other countries. This is some results actually from research work at UNAM, pointing out that Mexico is one of the countries that uses online social media more often. YouTube, Facebook, Twitter, Instagram. Of course, these are all platforms that are used quite frequently overall in the world and also in Mexico. At the same time, these are platforms where we humans tend to coexist with algorithms. And this poses some new challenges to political dynamics and to the formation of political beliefs. This is another report from the European Commission highlighting some of the challenges that online interactions pose to politics and to democracy. And one of the challenges pointed has to do with algorithmic content curation. And I'm just going to read what the report mentions. So of course that algorithms are an indispensable aspect of digital technologies, which can be used or abused to impact user satisfaction, engagement, political views, and awareness. And these curated news feeds, so the news that show up when you use Facebook, when you use Twitter, when you use social media, these curated news feeds and automated recommender systems are designed to maximize user attention by satisfying their preferences, which can mean highlighting polarizing, misleading, extremist, or otherwise problematic content. So this is an issue that was identified already in this report and in others, that algorithmic recommendation in these platforms might impact political dynamics and might exacerbate misinformation and polarization. So there's a lot of work on understanding how algorithms that filter contents impact polarization. But there is another class of algorithms that I believe that it is quite important in impacting our political beliefs and how we form opinions. And these are the so-called link recommendation algorithms. So link recommendation algorithms are algorithms used to recommend new connections to people in these networks. So in a way, these algorithms are used to recommend links to be established on these networks. So we have on Facebook, the people you may know, recommendations. On Twitter, we have the who to follow recommendations. So these are suggestions of who to connect with. This happens on Facebook, on Twitter, on TikTok, also in LinkedIn, we have the people you may know recommendations. So these are quite prevalent algorithms. Now, these algorithms are likely to impact our connections, but it is not immediately obvious how these algorithms are implemented. So there's no much information available online, and the exact code used by these algorithms is not publicly available. And this has triggered some passionate debates online. So people have been asking why certain recommendations are made. So again, the answer to this question is not obvious. There's not full transparency about how these algorithms are implemented. But we can learn, we can have some intuition for how these algorithms are, what they care about, what they use to do these recommendations, if we check some help pages of these platforms. For example, this is a blog post by Twitter from July 2010. So this is the date when Twitter introduced this tool, the who to know, who to follow recommendations. And when they introduced this tool, they also published a blog post where they point out that the suggestions of who to follow are based on several factors, including people you follow and the people they follow. So the point is that, of course, these recommendations might be based on information about common interests, but at a fundamental level, they are based on network properties, on how the network is structured. So if I follow someone, and if I follow the same people as a friend of mine, and if I don't follow everyone that he or she also follows, then I'm likely to be recommended the people that my friend also follows, for example. And this is a type of information that you can get only by looking to the network structure alone. Now, Facebook is a bit more clear. So Facebook in the help pages mentions that having friends in common is the most common reason for these suggestions to be made. Okay. Which makes some sense. So if I have a lot of friends in common with Professor Ricardo, and if we are not connected if we are not yet connected on Facebook, then we are likely to be recommended to each other. And the reason is that if we have a lot of friends in common, it is likely that we know each other in reality, or we have some interest to follow each other, so we are likely to be recommended. So the number of common, and this is an important point, the number of friends in common is likely to be one of the most important aspects of these algorithms. Okay. And knowing this, the goal of the study that I'm going to present you is to understand what is the impact of these algorithms on opinion polarization. Okay. So knowing that these algorithms are likely to recommend links based on the number of common connections, based on the number of common friends, what is the impact of algorithms like these on opinion polarization? Okay. This is the key question that we'll try to answer in the next minutes. And to tackle this question, I will present you a model of opinion formation on top of a dynamic social network. Okay. And once again, I'm not entirely sure if you are familiar with these models of network theory, so you will learn more about this probably next week. So before going deep into the models that we have been developing, I will just give a very brief overview of networks and of opinion dynamics on top of networks. Okay. But just out of curiosity, are you familiar with opinion dynamics on networks? Is this something new? Okay, maybe it's something new. So I'll just, I will.
No, you go ahead. Don't worry.
Yeah, I will present just to clarify some of the terminology. So when we talk about a network, usually we discuss edges and nodes. So nodes are here represented by the circles. In the case of social media platforms, represent individuals, people. And an edge, a connection between two individuals, exists if these individuals are connected in the network, if they on Twitter follow each other, or on Facebook if they are friends with each other. Now, of course, this is a very intuitive representation of a network, but to do some mathematical treatment, we need to represent these networks with some mathematical objects. And often these networks are represented with adjacency matrices, which are matrices that represent who is connected with whom. Okay, so here we have a number of rows and a number of columns equal to the number of nodes that we have. And we have either zeros or ones. So we have a one if there's a link between the two corresponding nodes. Okay, so here, for example, you see that in red, there's a link between 0 and 1. So we have in this matrix a 1 in the entry 1, 0 or 0, 1. Okay. So there's no link between 1 and 3. So here, if we check 1, 3, there's a 0. Okay, so this is the idea of an adjacency matrix. It's a way to represent mathematically a network. And people have been studying how opinions evolve on top of these networks. One possibility to study opinion dynamics is to consider that the number of opinions is discrete. There's a finite number of opinions. For instance, in the simplest case, opinions are binary. There's only 2 options, here represented in -1 blue or 1 red. And we are interested in understanding how will opinions in this network evolve over time. So will we reach a state where everyone agrees, or will we reach a state of polarization where both opinions coexist? And one of the so we use xi to denote the opinion of node I. Okay, so x1 is 1 red, and x3 is -1 here represented in blue. So one of the most famous models to study opinion dynamics with discrete opinions is the so-called voter model. So the intuition for how this model works is the following. So we repeat, first select a node I at random. For example, select node 0. Then select a random neighbor of I that we will call j at random. For example, node 3. And then we assume that node I will adopt the opinion of j. So we will do xi equal to xj. So in this case, x0 equals to x3. So with this model, if we select 0 and if we select 3, then well, what would be the next opinion of 0? Any idea? So if the node selected is 3, then the next opinion of 0 will be blue, -1. If the next node to be selected is 1, then the opinion of 0 will remain the same, will remain in 0. Okay. So this is the voter model. And then people have been studying based on the network topology, what is the likelihood that we reach, or how fast we will reach a state where everyone has the same opinion. Now, there's also some models where opinions evolve at the same time as the network structure. And here, one of the most famous models is the so-called adaptive voter model. So in this case, what we do is, first we select a random node, at random. For instance, we select node 3. And then with the probability phi, we select a random link to be broken. Okay, so here, let's say that first we select 3, then we select a node to be broken, this node here in gray, and we will add a new link between 3 and the neighbor with the same opinion. Okay, so this happens, a rewire process will happen with probability phi. Otherwise, with probability 1 minus phi, node 3 will just update opinion as I presented before. Okay. But if we follow a model like this, so if first we select 3, if we break the tie with the red node, and if we add a link with someone with the same opinion, any guess what would be the next connection to be added with node 3? Any guess, even if it's a random guess, if anyone wants to just guess a number?
Number 2.
Yeah, exactly. So we are breaking the tie with the red node, and then we are going to add a node with someone with the same opinion. So in the next step of this model, the link that we will add will be between 3 and 2. Okay, so this way, the network is co-evolving with the opinions. And actually, what this model shows is that you can have, if rewiring happens fast enough, then we can have polarization emerging in the network. And these opinions so far have been discrete. So we have been considering just 2 options, either red or blue or -1, 1. But there's also some models where opinions are continuous, where again, we have 2 signs. We have a negative opinion or a positive opinion, red or blue. but there's also an intensity of how much an individual supports a certain opinion. Okay? So opinions are still, if the sign is still binary, so we are still studying things such as, are you pro or against gun control? Are you pro or against any political issue? But now we are also measuring how much you are pro or against a certain issue. Okay, and so here I'm representing that idea by having not only a color, red or blue, but also a color intensity. Okay, so the more intense is a color, the more someone believes about a certain idea, the higher is the magnitude of that opinion. And in this context, one of the most famous models that studies opinion dynamics when opinions are continuous is the so-called bounded confidence model. Okay, so in this model, we assume that there's a population with n agents, okay, n nodes. So in this case here, n is equal to 4. We just have a population of 4. And each node will have a continuous opinion xi. Then at each time step, 2 random nodes are chosen to meet. For instance, we can select here these node 0 and node 2. And then they will readjust their opinion when the difference of their opinion is smaller than a certain threshold d. So this is to implement the idea that if 2 individuals interact with each other, but if they have opinions that are very, very different, they are not going to influence each other. Okay, so they are so they disagree so much that they are not going to talk even. Okay, if the difference in their opinion is lower than d, then they will influence each other, and if they influence each other, they will converge. Their opinions will converge. Okay, so if we select here 0 and 2, then what happens is that if the difference in their opinions is lower than d, then the red node 0 will become a bit more blue, and the node red, this blue node 2 will become a bit more red. Okay, so they will converge. They will talk with each other, and they will convince each other about the benefits of their own opinions. Okay. So this was just a very short overview. First, to make ourselves familiar with what is the meaning of an edge, a node, also the meaning of an adjacency matrix, and 3 different types of models to study opinion dynamics. One with discrete opinions, another with discrete opinions where the network also changes over time, and the third one where opinions are continuous, okay, where we measure both the agreement about a certain subject, but also how much someone believes in a certain subject. Okay. So next I will present the model that we have been studying so far, but is there any question about these 3 models, or any point that was a bit more confusing? Okay, well, feel free to ask questions later on. So this said, I will present you now the type of models that we have been studying. And again, recall that our goal here will be to develop a model that gives us some intuition for what is the impact of link recommendation algorithms in opinion dynamics. Okay. So we assume that there is a population with n individuals, and these n individuals will be connected with a dynamic network. Okay, so their connections will be represented by an adjacency matrix A, like the one that I presented before, composed by 1s and 0s. But this adjacency matrix will vary over time. We will consider a dynamic network. And then we assume that each node will have an opinion x that will be continuous, and that can take any value hypothetically between -infinite and infinite. Okay? But this is a continuous opinion dynamic model, like the last one that I presented before. So this is all fairly generic, but the models that we have been considering have three key ingredients that I would like to tell you about. The first one is that we will assume that the links are going to be rewired in the network based on structural similarity. Okay, structural similarity is a concept that is often used in the link prediction literature. Okay, and one way to measure structural similarity, so how similar are two nodes based on a network properties, is to count the number of common connections. Okay, so here A and B have two friends in common. A and C only have one friend in common. So we can say that A and B are structurally more similar than A and C. So the model, we are going to consider that links are going to be rewired in a way that links are going to be preferentially added between nodes that are more similar. Okay, so that's the idea. And the way, the goal is to capture the way that link recommendations are made, where, as we have seen before, they tend to recommend nodes that share a high number of common friends. Second, we will assume that opinions will vary through social influence. Here we have this white node that is connected by nodes with a red opinion. So we will assume that this white node will become, over time, more and more red. Okay? So opinions will vary based on the links that exist in the network and the opinions of neighbors. And there is an important detail. We will assume that there will be two different types of nodes in the network. We will consider type 1 converging nodes and type 2 polarizing nodes. And these nodes will differ in how they will react to members of the outgroup. So the converging nodes represent the nodes that, when they are connected with members of the outgroup, they will converge to their opinion. Okay, so here you have an example. So you have this blue node connected with red nodes. So if this node is converging, this node will become more and more red over time. The polarizing nodes, however, represent the individuals that, when they are in touch with members of the outgroup, they will become more polarized. Okay? They will be even more reassured about their opinions. And this, I will point to some references. There's some recent work pointing out that in online social media, when people interact with opposing viewpoints, they tend to become more polarized. Okay. So the idea of the polarizing nodes is, for instance, in the US, if you have a Republican interacting with a Democrat, or a left-wing individual interacting with a right-wing individual, the idea is that polarizing individuals will end up the discussion even more polarized than they were before. Okay? And the converging nodes represent nodes that, when they interact with members of the other party, the other group, they will be somehow convinced about their ideas, so they will converge to their opinions. So these are the three main ingredients that are important for the models that we have been studying. And I would go in detail about each of these 3 points. Okay, so I'll start with how we are doing these rewiring. So to rewire links based on structural similarity, what we do is the following. We repeat these many times. So at each time step, we select a random node I, and we will rewire a link connected with I. So for that, first we select a random link connected with I to be broken. And second, we will add a link between I and a randomly selected node J that is selected with a probability Sij. Okay. So Sij is the probability that we select the link Ij to be added. The important thing to retain about this probability Sij is that it will depend on the number of common connections. Okay, so here Ni is the set of neighbors of I, and J is the set of neighbors of J. So this orange term represents the common friends between I and J. Okay. And what is important is that the dependence on this term will depend on this parameter eta. Okay, so eta will be a parameter that will control how much the rewiring process will depend on structural similarity. Okay, so how much rewiring will depend on the number of common friends. And this is a parameter that will be very important for the results that I will present next. It is so important that I will give you an example to make things more clear for what is the impact of this parameter. So let's say that we have this network and we must recommend a link for A to be connected with someone else. And we can either add link AB in blue, or we can add link AC in red. The probability of adding link AB or AC, based on this expression, is given by this plot here. So we have on the horizontal axis parameter eta, so the rewire similarity strength, how much rewiring depends on number of common friends. And on the vertical axis, we have a probability. So we can see that if eta is very high, then we will almost for sure add link AB. And the reason is that A shares 2 friends with B and only 1 friend with C. If eta is 0, then the number of common friends doesn't matter. We will add link AB or AC, both with a probability 0.5. Okay. So you see that by increasing eta, we are increasing the likelihood that links between nodes sharing many friends will be added. And our argument is that link recommendation algorithms will tend to increase this eta. Okay, so they will tend to increase links preferentially between nodes sharing high number of common friends. Okay. So this way of adding links is quite important for the results that I will present next. So is there any question or any comment about this way of adding links? Or is it plausible? Does it make sense to you? Okay, we can also discuss these later on in the end of the presentation. So this was about how links are rewired. Let me now tell you a bit about how opinions will vary over time. So as I mentioned, we consider that opinions will vary through social influence. So here we have this node I connected. Yes, so I think there is a...
Hay una pregunta, doctor, por favor.
Sí, Alfredo.
Alfredo, adelante.
I think you are still muted, Alfredo.
Aquí ahorita la mano, pero mejor me espero un poquito, porque ya estaba explicando otra parte.
Entonces, ¿puedo continuar?
Yes. You
Okay,
can
okay.
continue, yeah.
Okay. Yeah, but good. I mean, anytime, feel free to interrupt, even if it's to go a bit slower. Feel free to raise your hand. So I will tell you about how opinions will vary over time. Okay, so here, node I is connected with a lot of red nodes. Okay, so here this white color represents a neutral opinion. And so in the next time step, it makes sense that I will become closer to the opinion of their neighbors. Okay. So we assume that opinions will vary through social influence. If I'm connecting with someone with the same opinion as I have, I will exacerbate my opinion. I will be more assured about my opinion. If I'm interacting with someone with a different opinion, I will be less confident about my opinion. So this is the idea behind this expression. So this is the full expression that we consider for the way that opinions will vary over time. So this is what is the next opinion of node I in the next time step, time t plus 1. So the next opinion will depend on the current opinion that I have times some parameter between 0 and 1. So this is just to represent the idea that over time, if there's no social reinforcement, then over time opinions will tend to become more and more neutral. Okay, so we are multiplying the opinion by something that is lower than 1. And this is a parameter that is also convenient to guarantee that opinions will not diverge, will not go to infinite. Okay. And then what we are doing here in the second term is to consider social reinforcement of opinions. Okay, so is the impact of neighbors in the opinion of node I. We are summing for all nodes, but we are only considering the neighbors. So remember that A, this matrix, has 1 if 2 nodes are connected and has a 0 if 2 nodes are not connected. Okay, so we only consider the opinion of neighbors. We are inputting the opinion of neighbors xj inside this hyperbolic tangent. So hyperbolic tangent is something like this. And this is just to introduce the idea that there's some bounded effect on the impact of opinions. So even if opinions are very, very, very extreme, the impact that they have is bounded. Okay, so this hyperbolic tangent is limited between 1 and -1. And this is also useful to introduce the idea that individuals are more sensitive to changes in the opinions when opinions are moderate than when opinions are very extreme. So basically the idea is that if a certain opinion, people cannot tell the difference between opinions that are very, very extreme from opinions that are very, very, very extreme. Okay, so after some point, all opinions look the same. But if opinions are somehow moderate, if they are here closer to 0, then people will be able to tell the difference between all the subtleties of a moderate opinion. Okay. And then we also have a parameter alpha here that controls social influence. So if alpha is 0, this term is always 0, so there's no social influence at all. If alpha is high, then it means that there's a lot of social influence. So individuals will influence a lot each other, even if they have moderate opinions. Now, this way of updating opinions is not new. This appears in some other papers, has been extensively discussed in other papers. In fact, this first paper here uses a similar way of updating opinions, and this is the paper that I believe Alessio Franci presented back in April. Now, no need to, of course, memorize all the details of this expression. What is important to retain here is that by using this expression, we are using 2 key assumptions. We are implementing 2 assumptions. The first one is that individuals from the same group will reinforce their opinions. Okay, so if 2 right-wing individuals or 2 left-wing individuals interact with each other, then they will reinforce the opinions that they have about a certain subject. And this is the idea of group polarization that is studied a lot in social psychology. On the other hand, if 2 individuals from different groups interact, then they will moderate their opinions. Okay, so if a left-wing and a right-wing individual interact with each other, their opinions will become more moderate. They will understand better the viewpoints of each other. Okay, so these are the 2 main characteristics of this way of updating opinions that I believe is important to retain. As I mentioned, however, this is only part of the picture. So this corresponds to the converging nodes. But I told you before that we consider 2 types of reactions to outgroup members. We consider converging nodes, but we also consider polarizing nodes. Okay. So polarizing nodes are nodes that, even if they interact with members of the other group, they will become even more polarized. Okay? So if a left-wing or a right-wing individual interact with a member of the other spectrum, political spectrum, then these nodes will even become more radical in their opinions. And this is based on some recent evidence in social media, but also past works on the so-called backfire effect. And this is some literature that highlights that if individuals are exposed to opposing viewpoints in online social media, they can increase political, they can become even more polarized. Okay, so exposure to opposing views can increase political polarization. Okay. And we can slightly change the expression that we had before to implement this idea. So now this sigma x is the sign of x. It can be either -1 or 1, negative or positive. And by slightly changing this expression, then what we are implementing is the idea that, once again, intergroup contact will reinforce opinions. So there's still group polarization. So individuals from the same party, if they talk with each other, they will become more radical. But now, this time, for the polarizing nodes, we also assume that contacts between members of different groups will also reinforce opinions. Okay. So the converging nodes implement the expression that I presented before that combine these two principles. The polarizing nodes implement this expression, so they will always polarize. Even if they interact with members of the outgroup, they will always polarize. Okay. So this is the idea. So this was just to give you this overview of the models that we consider. So again, the three important components are, first, links are going to be rewired based on structural similarity, based on the number of common connections. And this is a way of emulating what link recommendation algorithms are incentivizing. Second, opinions will evolve based on social influence and based on group polarization. And third, there's this important distinction between converging nodes and polarizing nodes. Converging nodes, when they interact with members of the other group, will converge. Polarizing nodes, when they interact with members of the outgroup, will diverge even further. Okay. So this is what I wanted to tell you about the models. I will next tell you about some results, but before that, is there any question, any clarification about the model, any comment?
Fernando, I want to ask you something.
Yeah.
In your model, I see that you don't include some kind of susceptibility or tolerance for the members of the population. I mean, a resistance to change of opinion. Are you thinking in that, or is for next works?
That's an excellent question. So you mean tolerance in the sense that only individuals that tolerate each other influence each other, and
yes, but my point is, probably you are surrounded of people which think in different way than you, but you have a very strong resistance to change opinion, and you are still in the same position forever. But probably you have 2 or 3 people which think different, and you have a high susceptibility to change of opinion. Mm-hmm. I mean, add a parameter for each member of population that describes his resistance to change his opinion. That's what I think.
Oh, I see. That's an excellent point. So now we are assuming that in terms of tolerance and in terms of accessibility, every node is the same.
Okay.
But so, and what I will point is that even with a model like this, we can have polarization emerging. So maybe if you had tolerance, or if you have accessibility, you could even exacerbate a bit more polarization. Yeah. I think, but we didn't implement that. But that's an excellent point. Yeah. Okay. So the only distinction that we consider now between nodes are whether they are polarizing or converging, but they are, in terms of accessibility, they are all the same. Yeah. Thanks.
Okay, thanks.
Okay, so let me tell you now, let's give you an overview of the results that with a model like this we are obtaining. So first, these are just some baseline results. This is just some sanity check to make us know we trust in what we are doing, that that is reasonable for some basic parameters. So this is the scenario that happens when social influence is low and rewire is also not that strongly influenced by the number of common friends. So if social influence is low, then opinions will converge to a neutral consensus. So initially, this is a time series. So we have time on the horizontal axis. We have opinions on the vertical axis. Initially, opinions are sampled from this interval between -1 and 1. And then what we see is that over time, opinions will tend to become more neutral, and everyone will adopt, or almost everyone will adopt, this neutral opinion. And this can also be visualized here in the bottom, where we have the initial network. So we start from a network that is a small world network, and opinions are randomly assigned. So here, red represents a positive opinion, blue represents a negative opinion, white is a neutral opinion, and the color intensity represents the magnitude of opinions. So you can see that in the end of the simulation, our network will look like this. So the network remains connected, and everyone will have a neutral opinion, okay, an opinion close to 0. If we increase alpha, so if we increase the level of social influence that we have, then what we observe is that opinions will become more radical over time, but everyone still agrees. Okay, we still reach a consensus. Again, if you look here in the bottom, we start from a network where there are a lot of opinions sampled between -1 and 1. And then over time, because there's a high level of social influence, people will convince each other and they will end up converging to the same opinion. Okay, so we will end up with a network like this, where everyone, in this case, everyone adopts a negative opinion, but this is only based on initial conditions. It's also common to have the whole population converging to a setting where everyone has a positive opinion. What's important to retain here is that for both of these cases, our parameter eta is still low. So links are added between nodes preferentially that share a high number of common connections, but this is still a relatively weak dependence. What is interesting is what happens when we increase eta. So if we consider eta equal to 4, for instance, so if we consider a setting where almost only links between nodes sharing the highest number of common friends are added, then we will have polarization emerging in the network. And this happens because if you look here to this bottom panel, you see that by adding links preferentially between nodes that share many friends, then we will have these isolated modules emerging in the network. Okay? And these isolated modules are going to be create an environment that is convenient for polarization to emerge. So we will have now these two extreme viewpoints being stabilized in the population. This happens if we allow the network to become completely disconnected, but the same conclusion happens if we consider networks slightly larger with more nodes, and if we impose the constraint that the network should always remain connected. Okay, so here on the right, we have the result of a simulation where if a link is about to be broken, but if it will disconnect the network, then we don't allow that link to be removed. So also in that context, the network will have these well-defined modules that are connected, but are dense enough for polarization to emerge. Now, these are just the results of some single time series, and the goal is just to provide an intuition for why we are observing these results. And this is the big picture. This is what happens for many runs, many simulations, and a large number of combination of parameters. So here in the left, we have polarization, and we are measuring polarization as the standard deviation of opinions in the population. And we have on the horizontal axis alpha, so the level of social influence, and on the vertical axis eta. So how much the rewarding process depends on the number of common friends. On the right, we have the same axis, but we have radicalization. So this is the average absolute value of opinions in the population. Okay, so if this is higher, it means that opinions are more extreme. And each of these points corresponds to a combination of alpha and eta, and it corresponds to the average results over 100 rands, starting in random conditions. So the results before only corresponded to this x, but you can see that in general, what happens is that if eta is high, if both eta and alpha is high, then we are creating a setting where we have both high levels of polarization and high levels of radicalization. Okay? So here, yellow means high levels of polarization and radicalization. And this is the first result that I wanted to tell you about. So the conclusion here is that by connecting structurally similar nodes or nodes with many common friends, as link recommendation algorithms tend to do, then we will have independent modules emerging in the network that can sustain polarization. Now, the point is that so far, I'm only considering converging nodes. And once again, as I mentioned before, it is likely that in reality, there are different types of nodes in what concerns the reaction to members of the outgroup. Okay, so we can have converging nodes that converge to the opinion of the outgroup, but we can also have polarizing nodes. So what we are doing now is to assume that we will have converging nodes with a probability rho and polarizing nodes with a probability 1 minus rho. Okay, so what we do is, in the beginning of the simulation, we go over each node and we decide if a certain node is polarizing or converging with a certain probability. Okay, so with a probability rho, the node will be converging and will remain converging for the whole simulation time. Otherwise, the node will be polarizing and will remain polarizing for the whole simulation time. And what I'm representing here now is the results in terms of polarization once again. So we have here on the horizontal axis eta, so how much the rewarding process depends on the number of common friends. And now on the vertical axis, we have rho. So this is the fraction of converging nodes. If we are here in the top of this plot, we are in the setting where all nodes are converging. And this corresponds to the results that I presented before. If we are in the bottom, we are in a setting where all nodes are polarizing. Okay? So you can see that if all nodes are polarizing, then we always have high levels of polarization without surprise. If all nodes are converging, then we have the results that I presented before, where increasing eta increases the level of polarization. This represents polarization. On the right now, we have the plot of radicalization. Now, what is interesting to observe here is what happens when we have a coexistence of polarizing and converging nodes. So if we are here somewhere in the middle, if we have rho equal to 0.5. So this represents a setting where there's an equal number of converging and polarizing nodes. And if this is the case, what happens is that by increasing eta, so by having this type of algorithms, we will increase both the level of polarization and the level of radicalization in the population. Okay. Which is it's not immediately intuitive why this happens. So let's go back to our time series. Let's inspect some individual simulations, some individual runs to have an intuition for why that is the case. So the first result is what happens when all nodes are converging. Okay. So if all nodes are converging, and this is a plot that I showed before, and we are always considering a high level of social influence. So in that case, we will have consensus. Okay, the population will evolve to a state where everyone adopts the same opinion. And here in the bottom, I'm representing the converging nodes with circles and polarizing nodes with squares. So here, the whole network is composed of converging nodes, and this is the network in the end of the simulation. So in the end of the simulation, everyone will have the same opinion. Now, if all nodes are polarizing, so if rho is equal to 0, then we will have, well, without surprise, polarization. So now all nodes here are squares, so all nodes are polarizing. And remember that the polarizing nodes will always become more extreme over time. Okay, so based on the initial opinions that they have, they will just over time, regardless the type of contacts that they have, they will always become more extreme. So the nodes that are blue in the beginning will become more and more blue. The nodes that are red in the beginning will become more and more red. So in the end, we have this situation where we have high levels of polarization, even if the network remains connected. Now, what starts to become more interesting is what happens when we have a combination of polarizing and converging nodes. Okay, so now notice here in the network that we have some squares and some circles. Okay, we have rho equal to 0.5. So we have 50% of the nodes are polarizing, 50% are converging. What is interesting is that if we have this combination, then opinions will become more moderate. So the polarizing nodes will become either positive or negative. And then the converging nodes, because they are being influenced by the two sides, by the two types of polarizing nodes, they will become moderate. Okay, they will not become radical over time, as it happened here on the left, but they will remain moderate. Okay, which is an idea that it's not immediately intuitive. So this is the idea that if all nodes are converging, then opinions will become radical over time. If we have a mixture of polarizing and converging nodes, then overall, on average, opinions are more moderate. Now, this happens only for one reason, and the reason is that the converging nodes are being influenced by the positive and the negative polarizing nodes. Now, if once again we have a situation where we add links based on the number of common friends, so if we have these isolated modules once again, then what happens is that a lot of these converging nodes will be alone in some groups with polarizing nodes. And so they will become more extreme. So once again, the message is the following. If polarizing and converging nodes coexist, opinions become more moderate because converging nodes will be influenced by the two types of polarizing nodes. If we have these modules sustained by by link recommendation algorithms, then we have the risk that some converging nodes will only interact with polarizing nodes, as in this case here that I'm indicating, for example, or there. And so the converging nodes will also become more radical over time. So overall, by increasing eta, we are increasing both the level of polarization and the levels of radicalization. And once again, this happens if you consider small networks, if the networks remain disconnected, but also if the network remains connected and if we consider larger networks. So the second result that I wanted to highlight is the following. When converging and polarizing nodes coexist, then opinions will become more moderate over time. However, connecting structurally similar nodes or nodes sharing many friends will create independent modules where converging nodes might not be exposed to diverse opinions, and so they will also become more radical over time. Okay. And these are the results that I wanted to tell you about. Now to conclude, so these are all the results about the models that we have been exploring, but I just wanted to conclude to pose the question of, okay, the main conclusion that I presented so far is that these link recommendation algorithms, if they recommend links based on the number of common friends, they might increase polarization and radicalization. But the question is, in reality, are these algorithms actually impacting the way that links are created? So these algorithms are just recommendations. It is up to the people then to accept or reject the recommendation. So do these algorithms impact the social network topology? And the answer is yes. There's actually some really nice work pointing out that these algorithms have a strong impact on the topology of the network. So this is a paper by Jessica Su and co-authors from 2016, where they studied what happens to the creation of links when Twitter introduced who to follow recommendations. Okay, so here on the left, we have the daily number of new edges in the network, the new connections. So we see that we are, before the recommendations are added, we are here around 8 million or slightly below 8 million on average. And then somewhere here between these two dashed lines, the who to follow recommendations was introduced. So immediately there was this jump, okay, where now we started to have, on average, more than 9 million edges being added each day. So by introducing these link recommendation algorithms, there was an increase in the daily rate of creation of links. But what is also interesting is, and this is what is represented in this plot on the right, is that these links tended to close more triangles in the network. Okay, so a link closes a triangle if it is a link between nodes that have friends in common. Okay, so if I have one friend in common with Professor Rosa, for instance, if now there is a link between me and Rosa, then this closes a triangle. Okay, and what they show is that after these recommendations were added, then the number of triangles that are closed increases. Okay, so basically these links tended to be added between nodes sharing more friends, having more friends in common. And this is what happens on Twitter, but the same, there's also some data indicating similar results on Facebook. So this is a time series where you have in blue the number of triangles that are closed on average, and in red you have the number of links added. And somewhere here, the people you may know recommendations of Facebook was introduced. So after this point, then there were more links added, but importantly, there were more triangles closed. So links tended to be between individuals sharing a high number of friends. And this concludes the talk that I prepared to you. So let me just summarize what we have seen. So the main question that I posed here was, what is the impact of link recommendation algorithms on polarization? To do that, I presented you a model of opinion formation on dynamic social networks, and a model that assumes that there is group polarization. Individuals from the same group tend to, if they talk with each other, they tend to become more radical over time. And it is a model, more importantly, that assumes that links will be created based on number of common friends, which is, as we have seen in the previous slide, it is likely to be a feature used in link recommendation algorithms. We developed this model, we performed some simulations with this model, and then first of all, we conclude that connecting structurally similar nodes or nodes that share many friends will lead to independent modules that can sustain polarization. And second, we also observed that when converging and polarizing nodes coexist, then opinions will tend to become more moderate. However, this effect tends to be disturbed if, once again, we have a high eta. So if we connect structurally similar nodes, then we will have independent modules where converging nodes may not find opinion diversity, and so we can have higher levels of polarization and radicalization. And the bottom line is that we should pay more attention to these link recommendation algorithms. So these link recommendation algorithms, at least theoretically, can impact opinion polarization, and they can also at the same time be possibly used as an intervention mechanism to control polarization and radicalization. And with this, thanks a lot for the invitation to present to you, and thanks a lot for listening. The presentation is based on this reference here, so if you want to know more details, feel free to check. And yeah, there's plenty of time for questions. So, thanks.
Gracias, doctor. Y bueno, pasamos a la ronda de preguntas, comentarios. Ricardo.
No, a ver si alguien tiene preguntas. Vamos a esperar. ¿Preguntas?
Y si quieren, pueden preguntar en español. Yo puedo intentar comprender y...
No se animan.
I was curious to know if is anyone working on similar models of opinion dynamics?
Yes, I want to talk about you. We made a model a few years ago, and a student and I, but we don't use a network. We use a population. We've moved in an environment, a kind of a model similar to epidemics model for SIR models. You see people moving and so on. No, well, the point is, if you put a parameter for resistance to change, and we have only 2 groups initially, in some circumstance, in some values of this parameter, appears an oscillating behavior, meaning people stay some time in this group and later change to the other, later return to the first, and so on, which is incomplete. Probably you know the works of Serge Galam. Galam say that in this situation, if you have two groups, inevitably you should go to a convergence. Have you seen some oscillating behavior in some instance of your work?
Yeah, it's an excellent question. We don't observe. What happens is that when we consider some noise, sometimes it is the case that a noise in the creation of links, but also in randomly adopting another opinion. We see that sometimes when a mutant appears in a group, that group can be influenced and changed to the other side, for example. So, but this is only driven by noise and mutation. It's not like not a dynamics intrinsic to the system. That's also maybe because the SIR type of models, I know that they are quite used to study rumor propagation, in the sense that if an individual is recovered, let's say, that the individual won't be able to be influenced again, which is, which in principle, it's something that here we don't have. So there's always this chance that someone can be influenced by I'm not sure if that's one of the differences that might lead for these oscillating behaviors not to appear. But yeah, but only due to noise. But yeah, but that work seems very interesting.
Yeah. Okay, you have a question in the chat, Fernando.
So your results seem to contravene the classical theory of minority groups. The theory says that a divergent group will end up influencing a convergent group. Can you comment on these vicissitudes? Okay, so I'm not familiar with the theory of minority groups. By divergent group, you mean a group that diverged from the general opinion in the population? Is that the case?
Cruz Garcia, Lirio.
Yeah, if you want to give more details on those models, Cruz Garcia, that would be nice. But otherwise, I can also comment. So a similar thing happens in what we are considering, actually. So here, what happens is that, for instance, in this case here, I think if I understood correctly, what you meant by diverging groups are these polarizing nodes. So, I mean, diverging would also be a good name for this. So these are nodes that always, regardless who they interact with, they always become more polarized over time. And actually, these polarizing nodes are pushing the converging nodes with them, right? So it seems to be aligned with what you wrote in the chat. The point is that these converging nodes are being influenced by the polarizing nodes that go to a more positive opinion and the ones that go to a more negative opinion. Okay? But let's say, but if we have a setting where these polarizing nodes here in the bottom don't exist, then we will have exactly the effect that you are suggesting. So the polarizing nodes will become more polarized and they will push the converging nodes. So it seems, does that clarify? So it seems that it's not contradicting that much, that theory. In fact, it seems that it's quite aligned, if I understood correctly.
Okay. Other questions? Well, finally, Fernando, your model suggests some kind of some kind of politics in order to mitigate polarization. But what you suggest in the real world, according to the result of your models, in a situation where there is a strong polarization? Yes. For instance, United States right now, or Mexico, for instance.
Here, all the messages are very much directed to the governance of online social media platforms. And so actually, these link recommendation algorithms, in a way, one of the ideas that I wanted to convey is that they might be one area where, by tuning the algorithm carefully, we could place people in contact that are likely to become more moderate over time. So now there's not that much information on how these algorithms are created. So we know that there's some negative images associated with social media, and maybe part of that is that there's also the way that these recommendations are made based on content and based on connections might be driving some of these polarization effects. But by tuning these link recommendation algorithms in such a way that you make appealing for people of the different political spectrum to interact with each other, then maybe here you have one message for policymakers and for people interested in governing these platforms where they should look into. Like these algorithms should be not only look to make connections that people are likely to follow based on the number of common friends, but should maybe also do an effort to establish a connection between people that have viewpoints that are not necessarily in agreement.
Okay, thanks. Bueno, más
hay
preguntas.
otra en el chat.
Ok.
En el chat.
Y luego el doctor Salvador.
Ok, gracias, Rosy.
Okay, so the question in the chat is, do you think it is possible to periodize or make some sequency? Can you please explain, Alfred, what is the meaning of periodize or sequency? It's just because I don't understand the meaning of sequency.
Alfredo, tú lo que dices es hacer movimientos de polarización y convergencia consecutivos.
Sí, algo así. It's what you're saying, Ricardo. that perhaps you use well, I don't know how to say in English, but perhaps it's the frequency. You can do these movements of polarization and convergence. I don't know if it's possible in this model to have this, for example, if you have an intervention and then to realize that it's polarization and then convergence. It depends on the context that you are using. I don't know if there is a kind of comparison that you can use in these models, or just or it's just that that's determinate like that you're showing us this model. I don't know if you can tell us a little more.
Thank you.
Kind of.
Yeah, if I understood correctly, I think it's if it's somehow also possible to study these and the idea of convergence and divergence are not static over time. They may succeed over different periods, which is an excellent question and remark. And so we don't study that in the sense that these diverging and converging nodes in the network remain fixed over time. But I think that that's an excellent suggestion for some future work, where maybe the number of converging and diverging nodes that we have in the network might change over time. So maybe there are contexts where you have more converging nodes, but maybe over time you have more and more of these diverging nodes. And that, of course, that might change the dynamics a lot. I agree. Yeah. Does that help, Alfred? I'm not sure if this was the exact question that you were asking.
Okay.
Si me permite.
Salvador.
Doctor Salvador.
Gracias. Okay, Fernando, thank you very much for your presentation. I will speak in Spanish. I'm sorry.
Yeah.
And the question is the next. En México, en Estados Unidos y en el resto del mundo, la característica esencial de la economía y la política es la polarización. Y la polarización no es solo política, sino que tiene un sustento, un sustrato estructural en la economía. Entonces la pregunta es, ¿la polarización en sí misma es fructífera, productiva, negativa, destructiva, o necesariamente la humanidad, las sociedades, las naciones, los países están condenados por mucho tiempo, no sabemos hasta cuándo, a la polarización política y a la polarización económica? Es decir, es la polarización, son cadenas que la sociedad no puede romper, o de qué manera se puede buscar la convergencia constructiva, productiva, edificante en una sociedad capitalista como la que hoy priva en el mundo y en México, desde luego. Thank you very much for your answer.
Thank you very much. Muchas gracias, Dr. Salvador. I think it's a very insightful question and remark. I think I will answer in English, but I think I will miss a lot of Spanish words. It's a very important. Well, first, I I didn't want to convey the idea that polarization is something positive or negative. So I was discussing what happens in terms of polarization and radicalization without necessarily saying that polarization is always good or always bad. I think that's a very important point. There's this, in the 60s in the US, people were complaining that there was not enough polarization, that everyone from Republicans to Democrats seemed to agree, and there's papers and news pointing out opinions that people should actually become more polarized for democracy to be richer and to have debate. So now we are in this state where there's some negative connotation with polarization, but I also think that these negative or positive connotation with polarization is somehow transient and it varies over time. I think it's also on the ways to stop polarization, on the ways to break polarization in the way. I think the answer based on this work, and of course here I can answer based on this work, is very similar to the answer that I give to Professor Mancilla. That here I'm just providing potential ideas on how to use algorithmic recommendations to alleviate that level of polarization. And I think it's a fascinating question, the connection between political polarization and economic polarization. I have not worked myself on that specific subject. I have some colleagues that did, so I'll be happy to share some papers, some references on how even theoretically you can show that there's an important connection between the two, where economic polarization or strong inequality might create environments that are more susceptible to political polarization. And there is, I'm not sure if in next month or in a couple of weeks, there will be another seminar by Vitor Vasconcelos that I've been working with and following his work, and he will present exactly on how polarization affects cooperation in economic games. And what he will discuss is the idea that for some type of economic interactions, polarization can actually be beneficial. For some others, polarization can be detrimental. So it's a fascinating question, the understanding the links between political polarization and economic polarization. That I think, yeah, again, it's the topic of another full hour of discussion. But I will be happy to share the works that I mentioned on inequality and polarization if you are interested.
Okay, thank you very much, Fernando.
Muchas gracias por tu pregunta.
Ya no tenemos más preguntas en el chat, Ricardo.
Bueno, pues muchas gracias entonces, Fernando, por tu presentación muy interesante, muy iluminadora para mí. ¿Quién viene la semana